This is lecture V-2. If you're following along in the student note packet, we're on pages 4 and 5 today. We're going to walk through examples A through E as the lecture, and then the homework that goes along with this lecture are the problems at the bottom of page 5. Before we get into those examples, we're going to do a recap of bearing. Bearing is something we talked about in the last unit, but it's something we're going to use again in this unit. It's just another way to measure angles that are unlike the unit circle way to measure an angle. So let's start with this angle theta. This angle theta is 47 degrees, and we're going to work with theta as we would measure a regular unit circle angle. So 47 degrees, we're going to start on the positive x-axis. We'll go counterclockwise. 47 degrees looks something like this. It's just barely past the halfway mark in the first quadrant. Okay, so that's theta. Unit circle angle wise, start on the positive x-axis, go counterclockwise to measure a positive angle. Now, if we want to express this angle in bearing, though, there are two ways to express every angle in bearing. There's the first method and the second method. So the first method always starts on the North Pole. And then to measure positive angles, we go from the North Pole clockwise. So to get this angle theta, which is 47 degrees on our unit circle, into its bearing, we would measure the angle from true north or from the North Pole going clockwise. So this is the first angle that represents the bearing. So what is that angle? Well, that's just 90 minus 47. That's 43 degrees. So the first method of bearing gives us a bearing of 43 degrees. Then the second way that we can express the same angle is that second method of bearing where we pick a pole. So either we start on the North Pole or the South Pole, and then we move towards the east or to the west, and then it kind of gives us a direction there. So all of those angles in the second method are going to be less than 90 degrees, again, starting at either the North or the South Pole. So in this case, we could express this angle starting from the North Pole because we're in the first quadrant. We're not going to start at the South Pole. We're going to start at the North Pole. I'm going to call this bearing method 2, starting at the North Pole. And we're going to move, again, 43 degrees towards the east. Okay, and so that's the second way we could express this. Now, when we have angles in the first quadrant, bearing method 1 and method 2, those angles are going to be the same. So let's look at a different example. Let's look at theta, and we'll define theta as 321 degrees. Okay, so 321 degrees, if we're measuring using our unit circle, is going to be in the fourth quadrant, almost all the way around the circle, a little bit less than 40 degrees shy of 360. So that could be 321. Again, we measure from the positive x-axis going counterclockwise for theta. So there's 321 degrees. Now, that's not bearing because it's not starting on a pole, the North or the South Pole, so it's not method 2. It's also not method 1 because we're not starting at true north. So let's find the first method of bearing, which is starting from the true north. Again, measuring clockwise this time. So that first measure of bearing is going to start on that North Pole, go clockwise. Now we just need to figure out what this angle in here is in order to get that first bearing. We'll add that to 90. So that is just 360 minus 321. That's 39 degrees. So our first method of bearing, that angle there is then 90 plus 39 degrees. So that's 129 degrees in the first method. But then the second method is where things start to differ a little bit. So bearing method 2, again, we start at a pole, either the North or the South Pole. Now, because our angle is down here in the fourth quadrant, we're actually going to start on the South Pole this time. And this time, we're going to start on the South Pole. We're moving towards the east. So if we start on the South Pole, we move a certain angle towards the east. We just have to figure out what that angle is, and there's our second method of bearing. Now, that second method of bearing is just 90 minus 39, or 41 degrees. So south 41 degrees. East could also be another way to express this bearing. Not 49, sorry. 51, not 41. There we go. Okay, so 90 minus 39 degrees gives us 51 degrees. So south 51 degrees east, that's our second method of bearing. Okay, we're going to use these today. When we draw the diagrams for each of these problems, I recommend, highly recommend, you do the drawings pretty large. So take up space in your notebook, use a ruler or a protractor, some sort of straight edge, and something that's going to give you guys relatively accurate angles so that your diagrams are accurate. Because when you end up in the wrong quadrant with a diagram, things are going to get off a little bit. All right, so on page 4, this is our first example here. We're going to draw a diagram that represents movement 90 meters due south and then 40 meters at a bearing of 250. So we're in vectors here. We talked about the parallelogram method the last lecture, which was when we were given two vectors and the angle between them. And this time, we're not given that information. So we're using the tail to head method today. We're going to draw the first vector, and then from the head of that first vector, we're going to start the second vector. So that's that tail to head method. Okay, so we're going 90 meters due south first, which means we're going to start somewhere. We're going straight down. Due south is straight down. And then another 40 meters at a bearing of 250 degrees. So we're going to be going like down and kind of to the left, which means the first vector that I draw, I'm going to start that vector in the top right-hand corner of my screen. I always like to draw a compass, as some people put it, or just an X and Y axis to kind of give me better ideas of where the angles are here. Okay, so I'm going to try and color code. The first angle, or the first vector, we're going to draw 90 meters due south. I'll do that in purple. So 90 meters due south, that's going to go just straight down. Okay, remember every vector needs a tail and a head. So you need to make sure that you include the arrowhead on one side. And that vector has a length of 90 meters. Now, from that position, from the head of our first vector, that's where the tail of our second vector is going to go. That's where our second vector is going to originate or start, thus tail to head. So from the head of that second vector, again, I'm going to draw another compass or another set of axes here, and then I'm going to construct my second vector. So the second vector is 40 meters at a bearing of 250 degrees. So a couple of things. I'm going to have to make sure that the bearing is accurate. But then also, because our first vector was 90 meters, I want to make sure that my second vector is somewhat relative in size to the first. So 40 meters means we're going to draw a vector, a line that is at least half as long as the first vector there, just to be as accurate as possible. Okay, and again, it's going to sit at a bearing of 250 degrees. So let's talk about that bearing first. We're doing the first method of bearing here, which means we measure from true north and we go clockwise. So 250 degrees from true north. This is 180. We're going to be shy of 270. We're going to be 20 degrees shy of 270. So that's where 250 degrees is. I'm going to construct that second vector in the third quadrant then. Okay, so let's do that. And again, that vector is going to be half as long, about half as long as that first vector. There we go. Okay, also needs a tail and a head, and we're going to call that 40 meters because we were given the length of that vector. Okay, one thing I'm going to note here, I know that that is that angle 250 degrees, and that can just be really helpful when we start to kind of construct certain things. Okay, what we're doing is we're looking for the resultant vector. We're trying to figure out what the net distance traveled is. So that resultant vector I'm going to draw in red today. It's always going to start where our original location was and end where we ended after the full trip. So that's what the resultant vector looks like. And we are going to be solving for its magnitude, which means I'm going to put that in absolute values so we know we're solving for the magnitude or the length of that vector. The second thing we will also include, though, is its bearing from the starting point, which we will also work through. Okay, so we do have a triangle in here, and I know a couple of things about this triangle, so just filling in things that we know can be really useful. This tiny little angle in here is 20 degrees. All right, it's 270 minus 250, and then I know that this angle is 90. So we have this whole angle in here, this obtuse angle, has 110 degrees. So that can be really useful. And we also have two sides. So we have side, angle, side, which means we can really quickly use the law of cosines in order to solve for the magnitude of r. So I'm going to write that out. Right, magnitude of our resultant vector squared is equal to 40 squared plus 90 squared minus 2 times 40 times 90 times the cosine of the angle between them, which is 110 degrees. Okay, plug that into your calculator, take the square root. You should be getting something like 110.28 meters. So there's our distance. The second thing we need is the bearing from the starting place. And we're going to do it in method 1, clockwise from true north. And that's how we're going to express that. So here's how I'm going to draw the bearing so we know what we're actually solving for. From true north of our starting location, going clockwise until we hit our resultant vector, that's the bearing we're looking for. So if we can figure out this angle on the inside of the triangle, then I know that our bearing is just 180 plus alpha. Okay, we've got a toolkit of triangles here. There's different ways that we can go about solving for alpha. We have the resultant vector, so we could use the law of cosines because we have all three sides. We'll do law of sines just because I know I'm not solving for an obtuse angle. We already have one in the triangle. When I set the law of sines up, the sine of 110 degrees over the side across from it, 110.28, is equal to the sine of alpha over 40, the side length opposite alpha. So when I type alpha into my calculator, we're looking at the inverse sine of 40 times the sine of 110 degrees divided by 110.28. Don't forget to take the inverse sine because we're solving for an angle. We should be getting something like 19.93. So our bearing, remember, is that plus 180. So something like 199.93. All right, so I'm going to write this all together. Our resultant vector has a magnitude that is 110.28 meters at a bearing of 199.93 degrees. And I will box that as the final answer there. All right, the second problem we have here is 400 miles west. So again, it's kind of like the due south one. Due west means we're going to be going straight to the left. And then from there, we'll go 248 miles at a bearing of 320 degrees. So the first vector is going to go left, and the second vector is going to go up and left with 320 degrees. So the first thing I'm going to do is I'm going to start my first vector all the way over here on the right-hand side of the screen, kind of at the bottom. And that just makes sure that I have enough room to draw everything in. So there's my compass, or my set of axes. And the first vector I'm going to do in purple here, so that's going to be 400 miles due west. So we're going to construct that vector first, just straight out like that. Remember that it needs a tail and a head, so the ending location is the head. And then that's 400 miles. Okay, from the head of that vector, first thing I'm going to do is going to construct another set of axes, or my compass. And then we're going to draw the second vector, which is 248 miles at a bearing of 320 degrees. So we have two things we need to get right. The length of this vector needs to be shorter than the length of the first vector because it is shorter. It's about maybe 2/3 the size. I don't know. Just do your best to kind of get as close as possible. If you have a ruler, you could do like 4 inches and 2.48 inches, and then you'd be pretty spot on. And then a bearing of 320 degrees. Now let's talk about that. Measuring from true north again, going clockwise, 320 degrees is going to be up here in the second quadrant. We're going to be 40 degrees shy of a full circle. So I'm going to draw that second vector now. Make it a little bit shorter than the first. Bearing of 320 degrees. Goes just a little bit past halfway. There we go. Okay. And that is 248 miles. All right. I'm not going to draw in that whole 320 degree angle because it goes through part of the diagram, but I am going to fill in this part. That's 40 degrees. And then what we're solving for again is the bearing and the length of our resultant vectors. So the net distance traveled That's our magnitude, and then we need the bearing of this vector as well. Okay, so what do we know? Well, this is 90 degrees, which means this angle in here is 90 plus 40. It's 130 degrees. So again, same thing we did last time. I'm going to use the law of cosines to really quickly solve for the magnitude of this vector. So the magnitude of this vector squared is equal to 400 squared plus 248 squared minus 2 times 400 times 248 times the cosine of the angle between them, which is 130 degrees. When I plug that into the calculator, don't forget to take the square root. We get something like 590.79 miles. Okay, so there's our magnitude. The last thing we need is the bearing. Again, we go back to the starting location. That's the bearing we're looking for. So measuring from true north, going clockwise, we need that whole entire angle there that I just marked, which means, again, same thing. We need to figure out what that angle is in there. And then our bearing is just 270 degrees plus alpha. Again, different ways you can go about solving for alpha. You could use the law of cosines because you have all three sides of the triangle all set up, law of sine, so we see both of them being used here. The sine of 130 degrees over 590.79 is equal to the sine of alpha over 248. So alpha is equal to the inverse sine of 248 times the sine of 130 degrees divided by 590.79. Don't forget to take the inverse sine. Make sure your calculator is in the right mode. When you get your answer, it should look something like this, 18.76 degrees. So the bearing we're looking for is 270 plus that, about 288.76 degrees. So I'm going to write it all together. Our resultant vector has a magnitude of 590.79 miles at a bearing of 288.76 degrees. There you go. Before we move on to the last two examples on the last page, I want you guys to pause this video and try C on your own. And then when you're done, come back. I'll have the answers up. Okay, there's the answer for C. The magnitude of the resultant vector is 33.78 kilometers. It has a bearing of 141.45 degrees. If you are interested in seeing the fully worked out solution, including the diagram, just take a look at the lecture slides that I posted on the class website. We're going to move on to examples D and E. All right, the last two examples here on page 5 are the trickiest ones, partly because of the second part of this problem, D, and then also the diagrams get a little tricky here. So we have a situation where Robert leaves home. He goes 8 miles at a bearing of 240 degrees, and then he turns and walks 13 miles on a bearing of 165 degrees. We want to find his displacement, the displacement vector as distance and bearing. So we need to find the magnitude of the net distance traveled and then the bearing from the original position. So the first vector is that 8 miles at a bearing of 240 degrees. So if I'm just thinking about 240 degrees in my head, with bearing, 240 degrees is going to put us somewhere in the third quadrant. We're going to be moving kind of down and left. And then from there, the second vector, 13 miles at a bearing of 165 degrees, that's going to put us in the fourth quadrant. So again, we're going to be moving kind of down, but to the right. So my first vector, I'm just going to start it kind of here in the middle top. And I'll draw that with a purple line so you guys can see the color coding here. 8 miles is the shorter of the two vectors because then the second vector is 13 miles long. So I just want to make sure I keep that in mind. The first vector is going to be shorter at a bearing of 240 degrees. So again, if we're thinking about bearings, starting from true north, 240 degrees is going to be 30 degrees shy of 270 degrees. So we're down here in the third quadrant, what we would call the third quadrant. Okay, so 30 degrees shy of 270 degrees, looks something like that. Needs a head on it. I'm going to mark the magnitude, and then I'm just going to mark this angle because I know what it is. It's 30 degrees. It's 270 minus 240. Okay, because we're using tail to head method again, I'm going to construct another set of axes. The goal here is to make sure that your axes that you're constructing are always parallel to each other. So like the north poles are always parallel to each other, right? And east and west always parallel to each other. Okay, from there, the second vector is going to be 13 miles at a bearing of 165 degrees. So we're going bigger this time. I'm going to color code this so it's green. 165 degrees is 15 degrees shy of the 180 mark. So from true north, we're going to go really, really close to 180, almost imperceptible. And we're going to make sure also that it's longer than that 8 miles. So I'm actually going to need to stick out down there in the second problem. That's that 15 degrees. And this is 13 miles. Okay, my vector also needs a tail and a head. So I need an arrowhead in one location there. And then the resultant vector is from the start to where we ended. We are looking for the magnitude of that vector and its direction or bearing. All right, well, what do we know? Okay, a couple things. With the purple vector, that first vector that I drew, we have alternate interior angles. So if that upper right angle is 30 degrees, then the bottom left is also 30 degrees. And then I know that this angle in here is just 90 minus 15. So that angle is 75 degrees. So total, we do have the interior angle here, 105 degrees is that big obtuse angle. So similar to what we've been doing, we can use the law of cosines really quickly to solve for the magnitude of the resultant vector. Okay, that's 8 squared plus 13 squared minus 2 times 8 times 13 times the cosine of 105 degrees. Don't forget to square root that in your calculator. Our magnitude here is going to be something like 16.94 miles. Slightly more complex here is the bearing. What we're solving for, let me mark it in red. From true north going down to that vector that represents our resultant vector, that's our bearing. There's not really an easy way to solve for this really, really tiny angle in here. So I'm going to have to approach this a little bit differently. If we can figure out this angle alpha, which we've been doing in the last couple of problems, then what do I know about our bearing? Well, if we can figure out alpha, then one way we can approach this is that our bearing is 270 degrees minus 30 minus alpha. So that's one option. You could have also said it's 240 minus alpha, right, which is 270 minus 30, but that's just kind of how I'm seeing it. So let's find alpha, and then we will just calculate that. We can find alpha. We've been doing it in the last couple of problems. I'm going to use the law of sines again. Sine of 105 degrees over the side opposite that, 16.94, is equal to the sine of alpha over 13. Okay, alpha is equal to the inverse sine of 13 times the sine of 105 divided by 16.94, which is going to give us something like 47.85 degrees. All right, so the bearing then is going to be 270 minus 30 degrees minus 47.85, which is looking like 192.15 degrees. Okay, and I just plugged it in there. Okay, so that is our resultant vectors, distance and bearing. Then there's a second part to this problem that says if Robert wants to walk back home from his current location, along what bearing should he walk? So Robert, I'm going to go back to our original diagram. Robert ends down here, right? That's where he is. And so we want to know on what bearing should he walk to get back home. So the last thing I'm going to do is I'm actually going to construct one more set of axes here, right at that resultant vector's head. And the bearing we're looking for is this little tiny angle between the North Pole and that red resultant vector. That is what we are looking for. It's very, very, very small. Okay, so a couple of things we can note here, and I'm going to try and change the color so it's really bright. This tiny angle up here is the same thing as this angle down here. These two angles They are equal to one another because they're alternate interior angles. So we can find that tiny angle there. Let's call it phi. It's just 90 minus 30 minus alpha. Because all of these angles together make up that 90-degree angle. And we have alpha already. We just solved for it above. So phi is equal to 90 minus 30 minus 47.85. Which is 12.15 degrees. So the bearing of the return trip home is 12.15 degrees. That's it. We're not asked for any other information there. But that is the bearing along which he should walk. The last problem here is a little bit different. So we'll see where we're going. Information we're given. So Bobby flies 45 miles an hour along a bearing of 312 degrees. And then the air is moving with a wind speed of 17 miles an hour along a bearing of 190 degrees. We want to find his resultant velocity, so the speed and the bearing, by adding these two vectors together. So we're doing the same thing as we were doing above, but instead of writing everything in terms of distance, we're now using miles per hour, using rate. Okay. So let's first construct Bobby's bearing, the 45 miles an hour along a bearing of 312 degrees. So 312 degrees is going to put us in what we would call the second quadrant. So that's moving up and to the left. So my first vector, I'm going to start from the bottom right-hand side of my screen so that I have enough room to kind of construct everything else. All right, so let's color code. 45 miles at a bearing of 312 degrees. So 312 degrees is 48 degrees shy of 360. So I'm not going to be halfway through the second quadrant. I'll be close, going clockwise. Okay, something like that. There's my head. Remember, this is a vector that represents 45 miles an hour. And I know a couple of things, but this angle has to be 48 degrees. It is 360 minus 312. Okay, then the air, let's see if I have to move this diagram a little bit. The air has a speed of 17 miles an hour, so a significantly smaller vector on that one, along a bearing of 190. So 190 is going to put us in what we would call the third quadrant, so that's going to be down, which is perfect. Okay, 17 miles along a bearing of 190 degrees. Okay, 190, kind of hard to construct. It's really, really, really close to 180. 17 miles an hour is going to be a relatively short vector in comparison to the 45 mile an hour vector. And I know that this angle in here, that's 10 degrees, right? That's how we got to 190, 180 plus 10. Okay, and the resultant vector then from our original start to the finish looks like that. Okay, so when we find the magnitude of that vector, that is the speed at which Bobby is actually traveling, and then we'll find the bearing along which he flies as well. What else do we know here? So let's kind of fill in the blanks. We have some alternate interior angles. If the angle here down here is 48 degrees, this is also 48 degrees, which means this entire angle is 58 degrees. So immediately we can use the law of cosines to find the resultant vector, the magnitude of the resultant vector. So that's going to be 17 squared plus 45 squared minus 2 times 17 times 45 times the cosine of the angle between them, 58 degrees. Take the square root, make sure your calculator is in degrees, and we get something like 38.77 miles an hour. So that's how fast he actually flies when he has to meet with the resistance of the wind. Now we need to know also along what bearing he's actually flying. So he's flying like into the wind, so he gets moved a little bit. And that bearing I will mark in red here. Again, starting from where we began, from true north going clockwise, that's the bearing that we're solving for. Okay, So what can we do? Well, kind of same thing we've done with the other problems. We can find alpha. We can find this angle inside of our triangle. And then the bearing is just going to be 360 minus 48 minus alpha. That's how I see it. Okay, when you clean it up, that's just 312 minus alpha. Okay, so let's find alpha. Now, we have to be very careful here. We've done everything that we can to make sure that our diagram is drawn as accurately as possible. So when I look at this diagram and I'm looking at alpha, I'm pretty sure that alpha is not the obtuse angle here. The way that we've constructed this diagram, this is the angle that looks obtuse. But I just need to make sure that you guys are doing that mental check to just make sure if you're going to use the law of sines that you are checking to make sure that the angle you're solving for is not obtuse. I am confident that alpha is not the obtuse angle in this triangle. So I am going to, again, use the law of sines. If you were worried about it, you could use the law of cosines to be perfectly fine. Okay, the sine of 58 degrees over 38.77. And you guys, please actually store values in your calculator and carry the decimals larger than that. I'm just writing everything out with the information that I have here. Okay, over the sine of alpha, equals to the sine of alpha over the side opposite alpha, which is 17. So when I plug this into the calculator, I'm plugging in the inverse sine of 17 times the sine of 58, all divided by 38.77. But I'm using the stored values in my calculator, okay, and alpha is going to give us something like 21.83 degrees. That is not our bearing. Remember that our bearing is 312 minus that. Our bearing is actually 290.17. Okay, so Bobby the bird is actually flying at a speed of 38.77 miles per hour, and he is actually on the bearing 290.17 degrees instead of that 312 degrees, which he was trying for. So there you go. Your homework that matches this lecture are then the problems at the very bottom. Do all of your work on a separate piece of paper. Draw your diagrams as large and accurate as possible. Make sure that you include diagrams so you get full credit. And if you've got any questions, just shoot me an email.